Namaste. So, let us now start the lecture number 3 of week 9 in this course of physics of nanomaterials. In this week, we are talking about self assembly and arrays of nanoparticles, which can have very different properties when compared to bulk. We have been talking about various types of assemblies which are possible and how does the assembly affect the properties have been discussed in the first two lectures. In today's lecture, let us discuss about monolayer formations and can we also induce behavior of porous like materials in such self assembled nanostructures. So, we will talk about the self assembled monolayers. How do we obtain these monolayers? Because what are we talking about? If you have a substrate, then you have one layer of material or particles which are self assembled, and this means all the material or all the particles which constitute this layer are going to take part in the reaction which you may infuse at the interface. So, it becomes very interesting to understand how do you get such monolayers. Are they difficult, or you have very simple strategies by which you can get such monolayers? You will find that forming such ordered monolayers is a very simple technique once you optimize the parameters which are associated with those techniques. Sometimes porosity in materials, that means the materials are not fully dense, but they have some porous structures which are intrinsically present within the material. That means you have some structures which gives you porosity. Can you have these structures and are they useful? We will take an example of a molecular sieve and then understand why porous materials are also arranged in a way that they are classified in these self assembled structures and they are also useful for various applications. So, we will start with the preparation of porous materials and we will also discuss some of the important applications of these porous materials. If you look into a monolayer, so what it actually looks like. So, you can have a typical self assembled monolayer formed on a gold substrate. So, you have a gold substrate on which you have formed a monolayer. For example, you have taken a surface active head group which will attach to gold, then you have a hydrophobic body of this molecule and finally, the terminal group, that is the terminal group of this functional group. So, you have these structures which are attaching to gold, and they are single layer formation. So, there is no another surface active group which is attaching here. You are talking about surface active head group which is attaching on the substrate. Langmuir-Blodgett technique is a very common and easy technique to obtain such self assemblies, and it has been widely used to obtain optical coatings, biosensors, ligand stabilized copper clusters, antibodies and enzymes. So, it basically involves clusters which form into a monolayer at an air water interface, and then these are transferred to a substrate in a form what is called as Langmuir-Blodgett film. So, basically what you do, you have a trough in which you have water system and suspended nanoparticles in them, and then you take a film and dip it and then bring it out. So, that is a controlled process by which you can deposit one layer at a time. You have this action taking place. So, these films sometimes can be difficult to fabricate and may not be as robust as you want. But if you consider the self assembled monolayers, these would be intrinsically stronger, stable and would not require external energy to self assemble in a given manner. That is the fundamental description we have been using for self assemblies, and hence you can make wide variety of materials using such techniques. So, for example, you can get these SAMs or even multi layers. So, if you arrange and repeat this process many times, then you get multi layers. Then you can get various types of metallic or catalytic particles depositing on metallic or even inorganic substrates, such as you can have deposition of silver, gold, copper, germanium, platinum, silicon, gallium arsenide, silicon dioxide, titanium dioxide, zinc oxide and so on. But the fundamental aspect remains the same. What is that? You must utilize that the bonding molecules or ligands such as alkane thiols or sulfides, disulfides, acids or siloxanes are used so that they can bond, for example, a thiol radical or an acid radical. So, now you use some kind of a bonding molecule which will bond the adsorbing surface with the incoming system which will get deposited on it. So, the binding to the surface for a thiol sulphide or disulphides is, for example, using sulfur atoms, and the entity, for example, RsAu is formed on a gold substrate, and the binding for the acid would then be RCO2 and MON, where MO denotes the metal oxide substrate ion, and here the hydrogen atom of the acid is released at the formation of the bond. So, you can have various atoms which will drive these bonding between the substrate and the atoms which would be getting deposited on such substrates. For example, if you use like alkane thiols, they are widely used ligands because they have higher solubility and their compatibility with many organic functional groups is also advantageous, along with the intrinsic benefit that their speed of reactions are also high. So, they spontaneously adsorb on the surface, and once you self adsorb on the surface, they are self assembling on the surfaces. So, they spontaneously adsorb on the surface and drive the self assembly. So, for example, you can take some thiol ligands and you can have different terminal groups and different n values, that is the chain length, and then you can see what happens to the material which is formed. So, if you have first the formation of the gold substrate. So, to prepare a gold substrate which will be acting as an extended site for cell assembly, because these atoms are not going to remain suspended in a solution. They have to get deposited on something. This is called as substrate. So, before something gets deposited on the surface, this substrates need to be made or functionalized in such a manner they are able to adsorb the incoming atoms, molecules, or any entity which would be self assembling on the surface. So, you take a gold substrate and use an electron beam or high temperature heating element to evaporate the polycrystalline layer of gold, that is approximately 5 to 300 nanometer thick, onto a polished glass slide, a silicon wafer or mica. Now, the outermost gold layer, although it is polycrystalline because it has come from a polycrystalline layer of gold, what does it do? It exposes local regions of planar hexagonal close packed atom arrangement. So, this is on the top and therefore, it is exposed, and various properties such as conductivity, opacity, domain size, surface roughness of the film depends on the thickness of this layer and the size and dimensions of this layer. So, now you have got a gold substrate on a glass slide. These adsorption sites are where are in the hollow depression between the triplets of gold atoms on the surface. So, if you take triplets of gold atoms, so if you take triplets for example, then if you look in the region, even if you have a closed packed structure, there would be a region which would remain unfilled. So, this region which is in the middle here becomes a hollow depression region. Now, the number of depressions is the same as the number of gold atoms on the surface. So, sometimes chromium or titanium is added to facilitate the addition. Now, what you have? When molecules in the liquid or vapor phase come into the contact with the substrate, they are spontaneously adsorbed on the clean gold surface in an ordered manner. That is, they also self assemble. Now, what will happen? When there is a self assembly, what are you seeing? The mechanism which would drive this adsorption will involve each particle of the alkane thiol molecule which will lose its hydrogen on its sulfhydryl group and acquire a negative charge, leading to its adherence to the surface as a thiolate compound by embedding its terminal sulfur group into the hollow depression between the triplet of gold atoms. So, now the sulfur starts occupying these hollow depression space between the triplet of oxygen or gold atoms. So, the S atoms, that is the sulfur atoms, start to deposit in the hollow depression layer between the triplet of gold atoms on the surface. So, this figure shows the mechanism of self assembly. The reactions can be written as you have the outer layer of gold film which contains M atoms. So, you have M gold atoms. So, once you have for spaces are between 3 gold atoms. So, you have the quantity Au plus M is positively charged triplet of gold atoms that are forming the hollow depression, where the terminal S negative forms a bond with the gold. So, effectively the charges in this region drive the deposition of the negative sulfur atoms on it, and there is an addition, and as the self assembled gold layer has arrangement of these hollow depression layers which also appear to be self assembled and ordered fashion. Therefore, sulfur also deposits in a ordered fashion. Now, if you want to talk about ordered monolayers, what will happen? Similar to what we have been discussing, you will get the functional groups For example, you can take a thiolate molecules absorbed on the gold surface. Then you will find that the functional groups can attach at the end of the alkyne chains in place of the methyl groups such as acids, alcohol, amines, esters, fluorocarbons or nitriles. So, these esters are also used in such. So, the formation of ordered monolayers can also take place using thiolate molecules. So, you can have alkyl chains which can form some kind of a thiol layer, and here the functional groups can attach at the end of the alkyl chains in place of the methyl groups such as acids, alcohols, amines, esters, fluorocarbons or even nitriles. Now, as long as the layer are less than 6, they tend to exhibit a significant disorder, because there could be stresses which are seen in the layers which are getting deposited. But once the thickness becomes more than 6, then you have more regular deposition, but polycrystalline in nature with domains of different alkane twist angle. But if you give them a temperature, then there is transfer of thermal energy K beta T, and that can cause domains to alter their shape and size. So, that is one way by which you can get new types of self assembled materials. You have another type of structures which can give you interesting phenomena. Those are porous materials. These materials have high surface area, and you can have materials with voids or pores within the material. So, they increase the surface area as well as accessible surface area without the necessity of reducing the particle size. So, now once you have high surface area, along with that, if you allow the access to large number of particles, then the reactions would be higher. So, you can have examples like zeolites, which are well defined structures that contain regularly spaced cavities, which act as host sites for atoms or small molecules to get trapped. Or you can have molecular sieves, which are engineered porous materials that can filter molecules of specific size. So, you have different types of porous materials. You can have oxide based materials such as silicon dioxide, alumina, Al2O3, which can be synthesized with controlled pore structures. These materials can act as sponge at the nanometer or even up to the micrometer range, with pores in the nanometer range. The specific surface area of such porous solids is generally determined by adsorption desorption curves using a BET method, the Brunner-Emmett-Taylor method, which we will discuss in 11th week. So, now you can have structures which can self assemble. You can have structures which can give you porous substrates, and now we have studied earlier the catalysts. So, you can have heterogeneous catalyst which can be prepared using highly porous supports, thereby giving you very large surface areas. And hence, you can have high catalytic activity compared to the cases where such catalysts were prepared without using porous supports, which would result in a lower surface area. So, large number of materials or catalysts have been fabricated using porous supports. Then you can have molecular sieves which can filter out specific size of molecules through them. For example, you have organosilicate molecular sieves MCM 41, which has a mean pore diameter of approximately 40 angstrom. Now, if you introduce trimethyl salicyl groups into the structure, some of these silanol groups inside the pores are replaced. Now, if these are replaced, what happens? This reduces the pore volume and shifts the pore size towards even smaller diameters. So, you have the pore diameters which are smaller, and such modifications then allow you to have fine control over the pore size, which means that you can have even finer control on the materials which would be sieved out, and hence you can tailor the materials for specific catalytic or adsorption applications. But it is also important that you ensure that when you make such modification in the structures, then the material remains the same, or if it shows some changes, then what are the features that are getting modified should also be understood before they are applied for any application. So, for example, if you take a NMR spectra of MCM 41, which is before and after the treatment. Now, if you can see, there is a new chemical shift peak at approximately plus 12 ppm, which confirms the incorporation of the trimethyl silyl groups into the pore structure. This demonstrates how you have confirmed the formation of a chemical change in the porous material using techniques like NMR, because these are giving you features which shows that there is a chemical modification in the system. Now, you have cases where you can have materials which have high surface area, you can even have porous catalysts, and then you can make the use in various applications. So, large number of transition metal oxide based catalysts have been investigated to replace platinum, which is very expensive and has limited reserves. So, to overcome these limitations, oxide based catalysts have been discovered and are being used for various applications. And then you can prepare them at different temperatures, that is different calcination temperatures, and by that you can change the pore structures, pore volume and the porosity, and hence you can modulate the catalytic properties of these materials. This is a typical example of zirconium dioxide, and let us take an example of hydrous zirconia, which has a porous structure and high surface area. You will see that the surface area actually decreases if you start preparing the material above 450 degrees, because there is a new phase which gets stabilized above this. So, this is driven by the conversion of the amorphous silica zirconia dioxide to a low temperature tetragonal crystalline phase of zirconium dioxide. So, it is also clear that the synthesis temperatures has very severe impact on the surface area which you can obtain in these materials. They can tune the porosity, they can tune the density, and hence their catalytic activities can be tuned just by changing the calcination or formation temperature. For example, you can take Bi2MoO6 structure, where you can see that as a function of temperature, you will find that the crystal can have different sizes at different temperatures, and that results in reduced surface area, and you can get stable crystalline structures, but because of the aggregation which results out of such high temperature synthesis protocols, you can get the behavior where catalytic response is much lower. So, in this lecture, it is clear that you can get self assembled monolayers, you can get porous materials of catalytic materials, nanomaterials, you can get molecular sieves which can filter out specific sized molecules, and you can fine tune the response characteristic by changing the formation temperature. These are additional references which would be very useful for further understanding the topics which we have discussed in this lecture. So, I thank you for attending the third lecture of week 9. Thank you.